All right, chemists, so let's talk about my second favorite subject or topic, significant figures, or sig figs. Oftentimes I will abbreviate significant figures as just SF. All right, so scientists use significant figures and recognize significant figures in order to communicate the correct degree of accuracy in our measurements and calculations. So there's a set amount of rules um, to identify the number of significant figures within a measurement. And so we'll go through those here and I'll give some examples, but really it just takes practice in order to recognize, what digits are significant, which ones aren't, and how to use significant figures in calculations, which we will go over within this lecture video. All right, so the rules for identifying sig figs. The first rule is that all non-zero digits are significant. And I'll point out when trying to identify the number of significant figures, you want to count the number of digits, reading the number value from left to right. All right, so you just want to count the number of digits that there are. All right, and so the first rule here is that all non-zero digits are significant. So some examples, like the number 58, if we count the number of digits there, 5, 8, those are two digits, so this has two sig figs. Or a number like 589, there's three digits, so there's three sig figs there. Or we could have a much longer number, even if there's a decimal place within it, like 589.123. I don't know, just making up numbers off the top of my head. Here, there are 1, 2, 3, 4, 5, 6 non-zero digits. So this number, as written, has 6 significant figures. All right, so remember, we're reading digits left to right. That first rule is that all non-zero digits are significant. Now, where things get a little murky is when zeros are a part of your value or that number. So how zeros work, the first type of zero we can have is a zero that's like sandwiched in between other non-zero values. So we call this a trapped zero. So for example, the number 508. So that zero here is trapped between two non-zero digits. So this zero is significant. We can essentially treat it like a non-zero digit. So as written, 508 has three sig figs because that zero is trapped. Or a number like 10.01. Right? So this number, 10.01, has actually two trapped zeros, sandwiched between two non-zero digits, in this case 1. So as written, these trapped zeros are significant as well. So if we count the number of digits left to right, 1, 2, 3, 4. As written, 10.01 has 4 significant figures. Let's do one more example with this trapped zero thing. So let's say a number like 1.061. All right, again, we have a trapped zero here. I can highlight them. So here are our trapped zeros, and they count towards significant figures. So as written, 0.061 has four significant figures. All right. So that's one type of zero you can see, where it's a zero trapped within a value. So another type of zero are zeros that are at the beginning of a number. These are not significant. So for example, a zero at the beginning of a number is like 0.123. So that zero is just telling us that where that decimal point is, that this number is smaller than 1. So typically when you write small values like this, you want to put that zero there and write this number as 0.123 instead of 0.123, especially in your lab notebooks and things. You want to put that zero there because it tells you that this is a small number. Because if you were just reading these two numbers really quickly off of your laboratory notebook when you're writing down measurements, you might miss or you might not see that dot, that decimal place. So you might read this number as 123. But in fact, if you make the measurement and it's a small number and it's 0.123, we want to put that zero there to indicate that this is a small number. So in lab, make sure that or whenever you're reporting a value, that you put that placeholder 0 there for small values so it's easier to read. And you'll see that I always do that. So I'll point it out when you don't put those leading zeros. So I'll write that here. So what this 0 at the beginning of a number, these are called leading zeros, and they are never significant. All right, so our answer here for 0.123, that 0 doesn't count, so this has 3 sig figs. Oops, 3 sig figs. Or a number like 0.15, that has 2 sig figs. And then some other examples, something like 0.0068. So these zeros are also leading in this case. So they're at the beginning of a number, and it has a decimal place. So these zeros also are not significant. I'll write that, not significant. So as written, 0.0068 also has 2 sig figs. All right? Or a number like 0.000015. So these zeros are also not significant. So as written, this number has 2 sig figs because they are at the beginning, or they're leading the number. All right, and they just locate where that decimal place is. So the numbers that we really care about here are the numbers at the end. So in this case, 1, 5. Oh, let me write that. So this has 2 sig figs. Okay, let's look on to the next rule. Again, looking at zeros. So our fourth rule, zeros at the end of the number are significant only if that number contains a decimal point. So I'll give you an example. So if we have the number 123.0, all right? So 123.0, 123 without the point 0, that has 3 sig figs because it's all non-zero digits. But see how I took the time to write the point 0? Since I took that time to write point 0 at the end there, this 0 becomes significant. It is significant. That 0 is significant. So 103.0 has 4 sig figs. And then I'll write, versus just writing 123, right? I didn't take the time to write that point 0. So 123 as written has 3 sig figs, right? Or let's do another example. If I said 100, 100 as written has only one significant figure. Because if we look back at this rule here, it says zeros at the end of the number are significant only if that number contains a decimal place. So since 100 as written has no decimal place, this only has one sig fig. Or I could write it this way, versus 100.0. So since in this example I took that time to write the extra point 0 at the end, all those numbers become significant. All of the zeros and the non-zero digit at the beginning. 100.0 has 4 sig figs. Right, this is something that really tests the bounds of significant figure identifying for students. Let's just do one more example because I feel like it. All right, so another example, let's say 0.2. 0.2. This follows our previous rule also because there's a leading 0 here, so that 0 is not significant. The only significant digit here is the 2. So as written, this has a 1 sig fig. But if I wanted to demonstrate better accuracy for whatever measurement I'm taking, if I wrote 0.200, because I took that time to write those extra zeros, as written, 0.200 has 3 sig figs. Because those 2 zeros at the end are significant because of the presence of that decimal place. So you can see how things kind of can get a little bit confusing with zeros at the end of a decimal place. All right, so that kind of brings us to number 5. So when a number ends in 0 but does not contain a decimal place, the zeros are generally not significant. So for example here, this last rule can be kind of problematic for large numbers. So let's say we have some type of measurement that's like 200. How can we, so as written, 200 has 1 sig fig, right? Because there's zeros at the end, there's no decimal place, so the only significant figure is 2. But what if I want to convey the number 200 but to two decimal places, or sorry, to two sig figs or to three sig figs? How would I write that? I mean, I could write 200 with four significant figures, writing it as 200.0. All right. So that has four sig figs. But what if I want to convey 200 with only two sig figs or three sig figs? So this is why scientists use the scientific notation. And that's where this next slide is. Scientific notation can help show clearly how many significant figures are in a certain value. So scientific notation, it typically takes on this form: a times 10 to some exponent. So the a portion of our scientific notation, we call this the coefficient. And a will always be some type of number between 1 and 10. So it will never be 10. So we always want to have one digit in the ones place for our a coefficient. So it's always between the numbers 1 and 10. And then that a digit or the a coefficient conveys all significant figures. Significant figures. B, that is our exponent. So this just tells us how large or small that value is that you're trying to convey. All right, so what do I have here? Scientific notation contains one non-zero digit to the left of the decimal place. So what that means is that this coefficient number a just needs to be between 1 and 10, that there's one non-zero digit to the left of the decimal place, essentially the ones place, that there's one digit in the ones place. All right, and so again, significant figure information is contained within the coefficient, so our a value. All right, and it's the magnitude of the value is given by the exponent, our b value. So magnitude meaning how big or how small our number is. So in general, with your b, that exponent part, if b is positive, a positive number, you're going to be taking 10 to a positive exponent. So when b is positive, we typically have a large number, like 200, 500, whatever, 5,000. When b is negative, we're trying to convey a small number. All right. So you might have looked at at scientific notation in high school or something, and saw when you have a positive b exponent, you move your decimal place from your a coefficient. You move your decimal place to the right to make the number bigger, your a value bigger. And then when b is negative, you move your decimal place to the left. So I don't like to memorize rights and lefts. I just remember, okay, when b is positive, it's a big number, so move your decimal place in the direction to make it a larger number. When b is negative, I don't like to memorize move the decimal place to the left because I get my lefts and rights mixed up all the time. I just think when b is negative, it's a small number, so move the decimal place in the direction to make the number smaller. All right, so that's when you're given scientific notation. Now let's think about how can we rewrite numbers into scientific notation, because then the lefts and rights kind of switch. So again, if you use your logic and just think, okay, when b is positive, your exponent's positive, that's a large number. When b is negative, you have a small number. Small meaning less than 1. So I'll say small number less than 1. All right, so let's rewrite some of these numbers and kind of think through the logic here to put them into scientific notation. So in this first number, 0.014, in my mind, I think it's a small number. That's a small number, it's less than 1, so our exponent will be negative. All right, so how I usually do this is I locate the decimal place and count how many places I would have to move the decimal place to make the a value between 1 and 10. So I'm going to move it one place, one place, two places. So now you see if I move the decimal place two places, that new number is 1.4. And see how 1.4 falls between our 1 and 10 uh, 1 and 10 criteria for our A coefficient value. All right, so there's only one number within the ones place. All right, so I wrote my coefficient. So now we need to determine, okay, what's the exponent off of the times 10 to the exponent. So if we count how many places we moved our decimal place, we moved it once, twice. All right, so, but because this is a small number, we need a negative number within our exponent. So to rewrite this number into scientific notation, it is 1.4 times 10 to the negative 2. Or you can think, okay, I moved that decimal place 2 times to the right, so it's a negative 2. All right, so let's keep going. So the next one, the next number, 370.0. So again, locate that decimal place, so it's right there. All right, and we want to move that decimal place so our coefficient becomes between 1 and 10. So you'll see, move it once, move it twice. So I'm going to move that decimal place two place values over to the left, making that number 3.7. But we also have to remember sig fig rules here. You can't just forget the rest of these zeros. So we need to think about significant figures. So 3 and 7, those are significant digits because they're non-zero. But because there's also a decimal place within this value, both of these zeros, these trailing zeros, are also significant. So to rewrite this correctly into scientific notation, we need to include those zeros because they follow our significant figure rules in the previous slide. All right, so there's our coefficient, 3.700. 3.700 falls between 1 and 10, so we're good with our coefficient. Now we need to write the exponent, so times 10 to the what? We move that decimal place over once, twice. All right, so this is going to be times 10 to the 2. So in my head, I think, okay, 300, that number is bigger than 1. All right, so it's a large number, so our coefficient will be positive. All right, lastly, this last number, so it's 500 million. All right, so 500 million, the question is, are those zeros significant or not? If we look back at our rules, there's no decimal places within this number as written. So no, those trailing zeros are not significant because there are no decimal places like in our previous example. But although I didn't write the decimal place, if we know that that decimal place would be right here at the end of the value, so we still have to kind of know where that decimal place is in order to move it to put this number into scientific notation. All right, so since those zeros are not significant, the only significant number is 5. So this only has one sig fig. That previous number that we just did that had 4 sig figs, and the first one we did had 2 sig figs. And so you see how we write it inside scientific notation. All of the significant digits are represented within that coefficient. Okay, so let's actually finish this. So let's count how many times over we need to move this decimal place to get our coefficient. So 1, 2, 3, 4, 5, 6, 7, 8. 8. So we have to move that decimal place over 8 times. So if we move it over 8 times, that coefficient becomes 5. All right, remember that this number only has one significant figure as written. So 5 only has one sig fig. All right, and let's do our exponent times 10 to the 8. And again, I like to think, okay, 500 million, that's a really big number, so our exponent will be positive. But let's say you wanted to express the number 500 million, but to 2 sig figs. How would you do that? Because that kind of brings us to this last point up here. Oops. This last rule is problematic for numbers like this, like 200. How can I express that in 1 versus 2 sig figs? So 500 million here as written only has one sig fig, but if we wanted to express 500 million as in 2 sig figs, all we would do is have to change the coefficient. So we could write it 5.0 times 10 to the 8. This number, as written in scientific notation, has 2 sig figs, while this first one only has 1 sig fig. If I wrote 5.00 times 10 to the 8, this has 3 sig figs. So you see how scientific notation is a more powerful tool to convey significant figures than just writing out large numbers like this. Because there's no way I could distinct make distinctions between 1, 2, or 3 sig figs, writing it like this, unless like I underlined the significant figures in those values. Okay, so that is the overview significant figures. So before we go into looking at significant figures within calculations, let's do a little bit of practice. So I've written here a bunch of numbers, and let's just see how many sig figs are present within a lot of these values. So let's go through some of them here. All right. So let's just work through them. So let's keep in mind those rules for identifying sig figs. So this first number, 17.45, those are all non-zero numbers. So this value, as written, has four sig figs. 1, 2, 3, 4. And in class, like in recitation, and within these lectures, typically what I do when I'm trying to convey significant figures in calculations or written values, I'll oftentimes underline the last significant figure. So that way, in my mind, when I'm reading that number left to right, I know that, oh, I can stop counting sig figs right here. So that might just be a nice type of thing that you do within your own work. All right, so that's that first number. The second number, 70.1. So we have a zero. Zeros always throw students in for a loop. This zero is a sandwiched zero, so that zero does count in terms of sig figs. So all those numbers as written are significant. So this number has 3 sig figs. All right, 9,007. Again, these are 2 sandwiched zeros. So this number as written has 4 sig figs. All right, I'm just going to skip around here. Let's look at these 2 examples. So these 2 numbers, they look the same. We have 0.003. All right, so these are leading zeros. So they do not count for sig figs. So the only significant figure here is that 3. So as written, 0.003 has 1 significant figure. Versus the other example here on the right, I've written it a little differently. It's 0.0030. So I wrote that 0 at the end, and because there's a decimal place present, that 0 becomes significant. So those end 2 numbers are significant. So as written, that number has 2 significant figures. All right, and so I have a bunch more examples here. All right, so let's look at some of these scientific notation ones at the bottom. So scientific notation is nice because it's all of the numbers contained within the coefficient, your a value, contains the significant figures. So it's quite easy. You just have to count how many numbers are there. So 6.3. This has 2 sig figs. You can just ignore the coefficient, or sorry, not the coefficient, the exponent. The exponent only tells you how large the number is. So you can kind of think of that as an exact value. We've talked about exact values before, and we say exact values have infinite number of sig figs. So you can think our b exponent is an exact value. So it has infinite sig figs. So we're only ever limited in sig figs that are contained within the coefficient. All right, so this next one, 4.00 times 10 to the 1. So remember, I took the time and wrote those zeros at the end. So all of these numbers, 4.00, are significant. So these are 3 sig figs. This is different than if I wrote something like 4 times 10 to the 1. If I wrote 4 times 10 to the 1, since I didn't take the time to put the 0.00 at the end, that only has 1 sig fig. All right, so I always like to encourage students to watch lecture videos. So almost within every chapter, I will put a little bit of extra credit within them for the students who are watching. So you see that, I didn't do all of the examples here, but if you, take a screenshot or copy down these values here and complete the rest of the identifying the number of sig figs, just email me your answers. So just, take a picture of your work on a piece of paper or whatever, email me the rest of these answers, and I will give you extra credit on your first midterm. So there's a 1, 2, 3, 4, 5, 6, 7, 8, 9. So do those 9 other identifying how many sig figs are in those numbers, and I will give you extra credit. So just email me these numbers. Just title it like extra credit chapter 1. All right, and I'll give you a point of extra credit on your midterm 1. Okay, so let's keep going. Now we're going to look at using significant figures. Oops, no, I have to go back here. Using significant figures within calculations. All right, so we did the first step, how to identify how many significant figures are within a value. So now we need to think about how do those significant figures carry out through a calculation. There's two rules. There's addition subtraction rules, and then there's multiplication division rules. Students get the multiplication division rules pretty well. It's the addition subtraction ones that students just like forget about. So let's go through those. All right. So for addition subtraction, when you're adding and subtracting measured values that have significant figures, when you do that calculation, you need to round your answer to the least significant decimal place, essentially meaning leftmost your leftmost placeholder or place value that is common to both values. So let's pretend we're just adding or subtracting two numbers. All right. So you want to round your answer. Your last significant digit will be the last decimal place or the last place value that both values have in common. So let me do a example here. One of the best ways to kind of look at addition subtraction is to, when you do the calculation, put the numbers on top of one another. So like if, let me think of an example. So like 89.32 plus 1.6. So in this example addition problem, the best way to kind of see where the significant figures lies in your answer is to put those numbers on top of one another. All right, so it's harder to see when you write the addition problem like this. So remember, like in grade school, when we add numbers, we put them on top of one another and we line up the decimal places. So if you rewrite the question like this and then go ahead and, plug that into your calculator and get your answer, if you plug that in, what will spit out of your calculator is 90.92. Okay, so now let's think about significant figures. So in both of these numbers, all of the numbers are significant. All right, so the last significant digit in 89.32 is that 2, and the last significant digit in 1.6 is the 6. But let's remember, look back at what this addition rule says, that we need to round our answer to the least significant decimal place. I'm going to say placeholder because it doesn't have to be a decimal place or place value. So you need to round to the leftmost or the last decimal place that all the values have in common. And I think it's easier to see when you put the numbers on top of one another. So if you look at those place values, if we look at the end here, because it's the end, we need to figure out, okay, where does the significance end in our answer? Both values have a number in the tenths place. So that means when we round this answer, we're going to round at the tenths place. So essentially, we're not, that 2 kind of gets left out. All right, so our answer here, when we round this, we're going to round at the tenths place. So our answer here is 90.9. All right, and so you can see, our first number has 4 significant figures, our second number has 2 significant figures, and our answer has 3 significant figures. And that's fine for addition subtraction. The number of significant figures can change, and it probably will be different than the values you put in. It's the multiplication division one that most students remember. It's like you just count up the number of sig figs and you round to the least number. That's the one students remember. It's the addition subtraction one students tend to forget. All right, so you need to look at the leftmost placeholder or place value that all of the numbers have in common. So in this case, it's the tenths place. So let's do another example. Let's do a subtraction question. So 15.68 minus 0.123 equals what? All right, and again, looking at significant figures for addition subtraction, just put the numbers on top of one another like we've done in grade school. So 15.68 minus 0.123. So you can see here, even before I put this into my calculator, you can see that both numbers have values in the hundredths place. So our answer will be rounded to the hundredths place. all right, since both of them have a value in the hundreds place. But let's, get the answer. So if you put that into your calculator, you get 15.557. All right. And so again, like I said, we're going to round to the hundredths place here. So our answer will be 15.56. So that's 7 because to the right of the where we're rounding is higher than 5, then we will round up. We will round our answer up. So the answer here is 15.56. This has 4 sig figs. All right. So in addition subtraction, you're never just counting sig figs. That is for multiplication division. And so those rules are here. So for multiplication division, when you perform those calculations, you need to count the number of significant figures and all the values that you put into your calculation. So you take whatever number has the least number of significant figures and you round your answer to that number of significant figures. So let's do a little example here. All right. So let's say 3.1 times 4.1. All right, so in this example, we have 3.1 times 4.1. Let's just plug that into your calculator. If you put that in your calculator, you get that this comes out to 12.71. All right, but if you put that answer on a test, I would mark that wrong and take off points for significant figures because you have not put any effort into trying to determine the number of significant figures in your answer. So to do this, to do significant figures in multiplication, you need to count the number of sig figs in both of your inputs in the values you're multiplying together. So 3.1, that has 2 sig figs. 4.1 also has 2 sig figs. So that means our answer needs to be rounded to 2 sig figs. All right. So to round to 2 sig figs, remember, we always count left to right. So 1 sig fig, 2 sig figs, we're going to round to the ones place here. And so if we round to the ones place, you see that that's 7. It will round 12.71 up to 13. So our answer here is 13. 13 as written has 2 sig figs. So this answer conveys the correct number of sig figs based upon the significant figures and the values you're putting in. All right, so let's do a division example, but again, it follows the same rules. So let's do 6.723 divided by 2.88. All right, so let's just stick that into our calculator and put down a number so we know what we're working with. So the answer here is 2.3343. So oftentimes when I'm doing a calculation, I'll just put a bunch of numbers down off of the calculator because my calculator gave me like a bunch of numbers. So I just put a little bit more than I'll need and then round in the next step where I need to. So let's identify the number of significant figures that we put into the values in this calculation. So 6.723 has 4 sig figs. 2.88 has 3 sig figs. So we're going to round our answer to 3 sig figs. So let's rewrite 2.3343, but only having 3 sig figs. So if we just read left to right, 1, 2, 3, we want to round right here at the hundredths place. So our answer written to 3 sig figs will be 2.33. And that's our answer. All right. So again, my tip for you is that most students can do the multiplication one. They can count the number of sig figs, round their answer to whatever number's lower. It's the addition subtraction one that will throw you for a loop. You need to look at what is the leftmost common placeholder that you need to round to in your answer. So let's do a little bit more practice with our 2 sets of rules with sig figs in calculation. So our first is addition subtraction. This is the one students have the most trouble remembering. All right, so I kind of just summarize the steps in which to do an addition subtraction sig fig calculation. So the way I go about it is first I identify the last significant digit in the values that you input into the calculation. So what I mean by last significant digit, I really just mean the rightmost digit. So first, just identify where those last digits lie. So if we look at this first example, here I see the last significant digit in 10.05 is that 5 in the hundreds place. In the other value, 212, that last digit is that 2, but it's in the ones place. All right, so what's the next step once you've identified that last or rightmost significant digit? Next, you want to do the calculation. So actually, in between the step here is do the calculation. And then you want to round your final answer to the leftmost place value from step 1. So what do I mean by that? So if you actually do this calculation, you get something like 222.05. That's the number that comes out of your calculator. And note how I um, have units here. So we're adding volumes. 10.05 milliliters, 212 milliliters. Gives us 222.05 milliliters. This number comes straight out of your calculator. But now let's look at significant figures. So I've identified the last rightmost significant figure in both of these values, but now I need to round my answer to whatever place value is the leftmost. So we have to think, also it's clearer to see if you put the numbers on top of one another. All right, so if I put the numbers on top of one another, so you see here, we have this 2 in 212 in the ones place and 10.05, that 5 is in the hundredths place. So where we're going to actually round is to the ones place. So the ones place in this case is that leftmost place from our first step. So we're going to round this number to the ones place. So that's often what I'll do. I'll denote what is the place value we round to in an addition subtraction problem. So in this case, we round to the ones place. So our final answer here will be 222 milliliters. Remember, every measured value has significant figures. It has a value that has significant figures, and it has a unit. So we can't forget that unit here, which is milliliters. Okay, so let's do another example. Again, we're adding volumes. So 3.8 plus 12.2 milliliters gives us what? So let's identify the last significant digit in both of those values. In this case, both numbers end in the tenths place. So we will round our answer to the tenths place. Great. So next, we actually do the calculation, stick it into our calculator. You stick those numbers in your calculator, you get 16. That's the number your calculator will spit out. But unfortunately, calculators are stupid when it comes to significant figures. So we have to, as scientists, convey the number of significant figures in this value. So we already decided that both these numbers end in the tenths place. So we need to round our answer to the tenths place. So even though the calculator did not spit out a digit in the tenths place, we need to put it there. So we need to convey the amount of confidence we have in this value. And so the correct answer here to the correct number of significant figures is actually 16.0 milliliters. So we actually have to add that 0 because both the digits that we put into this calculation end in the tenths place, so our answer also has to be conveyed to the tenths place, and that's what I have here. So just know, if you put numbers into your calculator, the calculator doesn't tell you sig figs. You have to use your logic and your sig fig rules to figure it out. Right? So there's an example where the calculator, you have to add essentially a significant figure to what the calculator says. All right. So let's do one more example. So subtraction this time, so we're going to subtract mass. So 1.008 grams minus 0.9671 grams. All right, so again, I'm going to identify that last significant digit. So in this case, it's to the thousandths place for 0.008. And then here it's to the fourth decimal place, so the 10,000ths place. So I want to choose the leftmost one. So again, if you put these numbers on top of each other, you can kind of see it. Oh, I should do it the other way. 0.9671 grams. All right. So you can see here, if you do the subtraction, we actually want to round to the thousandths place. We want to have 3 decimal places in our answer. All right. So keep that in mind. We're going to round to the thousandths place, the 3rd decimal place, because this 1.008 only goes out to the thousandths place. So if you stick that into your calculator, you get something like 0.0409 grams. Okay. So right now, as written, I usually keep a bunch of decimal places or a bunch of places before I round. All right, so but here we already decided that we are going to round to the thousandths place. So if I underline that in my answer here to just kind of tell myself, hey, I need to round to this decimal place. So our answer is 0.041 grams. That is our answer. All right. So again, you can see how the numbers that we put into this calculation, 1.008 has 4 sig figs, point 0.9 not 0.9671 has 4 sig figs, but our answer only has 2 sig figs because this is addition subtraction. We're not looking at number of sig figs. We are looking at where does the last significant figure lie? What placeholder does that or place value does that exist in? So in this case, both numbers are known to the thousandths place, so that's the number that that's the place value we round to. All right, so there's our answer. Okay, so the last part of sig figs and calculations is multiplication division. So this one's a little bit more straightforward for students. So with the rules for multiplication division, remember, is all you have to do is count the number of sig figs in each value, and then you want to round your final answer to the smallest, right? Is that what I want to say? The lowest number of sig figs from step one, right? So you just count them all up, pick the smallest one. That's the one students can get the most, or that they usually get correct most of the time. So some examples. So here's just a straightforward division problem. So usually what I do is in problems like this, I'll just write how many sig figs each value in each input we have, how many they have. So 89.1 has 3 sig figs, 88.56 has 4 sig figs. All right, and so if you put that into your calculator, you get 1.00609, and the unit there is grams per milliliter because we want to keep those units, right? But now let's look at those sig figs. So 3 sig figs, that's where we want to round our answer to because 3 is less than 4. So I'm going to round to 3 sig figs. So remember, we're going to count left to right, the numbers left to right. So 1, 2, 3. We're going to round to that third sig fig. So we're going to round, not truncate. So because the number to the right of that 0 is a 6, we're going to actually round that number up. So our answer to the correct number of sig figs is 1.01 grams per milliliter. Cool. That's division. Same thing with multiplication. So here we're multiplying 3 different lengths together to get an area, all in the unit of meters. So again, I just count number of sig figs. So different color. So 6.2 has 2 sig figs. 1.25 has 3 sig figs. 89 has 2 sig figs. So in this case, we're going to round our answer to 2 sig figs because 2 is less than 3. So if we stick that into our calculator, that number that you get out is 689.75 meters cubed. But we want to round to 2 sig figs. So let's count left to right. So 680. So we will round to the tens place in our answer. So to do that, we just look at the number to the right. Since it's a 9, we're going to round that place value up. So this rounds to 690 meters cubed. All right, but a better way to convey that would be to convey it in scientific notation, because you might think, does this have 2 sig figs? Does it have 3 sig figs? No, we want to convey that it has 2 sig figs. So probably the best way, where there's no confusion of how many sig figs 690 has, would be to write it 6.9 times 10 to the 2 meters cubed. That would be the best way to convey it, but 690 will work as well. All right. So that's multiplication division. Just add or identify the number of sig figs in all of the inputs. You just choose the smallest, lowest number, and that's where you round your answer to. So before I finish this lecture video, let's do kind of a combination of sig figs in a question. So taking an average of something. Let's pretend we want to take an average of like 3 people's heights. So let's look at the sig figs involved with taking an average. So let's say we want to take the average of 3 people's heights. Those heights are 4.9 feet, 6.0 feet, 5.5 feet, divided by 3. That's how you take the average. You take the number of values or number of measurements you take, or you add up all of the measurements and you divide by the number of measurements that you take. So in this case, since there's 3 measurements, we're going to divide by 3. So we can see what kind of operations there are here. We see that there's addition and there's division. So it's kind of like a combined operation. But in this case, it's different. It's a little bit of a trick question because 3. Think about what that 3 means. The definition of an average is you divide by the number of measurements. So we're counting number of measurements. So since we're taking the measurement of 3 people's heights, 3, I counted that number. So 3 in this case, in this average calculation, that is an exact number. So 3 actually has infinite number of sig figs. So the only significant figure operations that we care about are in the numerator, is in our addition. In our addition work. So when we end up taking the adding up all those heights, dividing by 3, this 3 is not going to affect our sig figs in our answer. So it does not affect sig figs in answer. So let's just do the problem. So if I take 4.9 plus 6.0 plus 5.5, that's 16.4 feet divided by 3. So I just did the work that's in the numerator. But let's look at sig figs here. This is addition. So if we look at all of the different inputs, all the different values, see how all of them end in the tenths place. So our answer there also has to end in the tenths place. So that number that we just did has 3 significant figures, the addition that we just did. So that means when we move on to the next step and divide by 3, which has infinite number of sig figs, so now we're doing multiplication division rules. Now we're taking a number with 3 sig figs, dividing by something with infinite sig figs, choose the lowest number. So our answer should have 3 sig figs. So if you do that, I didn't even have the answer in front of me. So 16.4 divided by 3 is 5.466 feet. Right? So I said that I want to round to 3 sig figs. So right there. So our answer is going to be 5.47 feet. So you might see here that each of the numbers we put in only go out to the tenths place. But if we follow sig fig rules correctly, average we get out actually goes one more decimal place further. It actually goes to the hundredths place. And that's okay. So actually what this is kind of demonstrating why we do multiple trials of something, because we can gain significant figures or accuracy if we add a bunch of numbers together because of the rules of addition. So in this case, because we're adding 3 different numbers that end in the tenths place, all right, we're going from 2 sig figs in all these values. Our answer actually has 3 sig figs, so we gained a level of significance. We divide by 3, which is a counting number, so it has an infinite number of sig figs. So our answer goes out to 3 sig figs. So here's a way that scientists can actually increase the number of sig figs and accuracy within their answers. All right, so that kind of demonstrates, the power of addition sig fig rules, and how it's useful for chemists in lab.